To end this learning sequence, we're going to talk about magnetism in matter, an extremely complicated subject. I have several times drawn bar magnets and told you they're magnetic because they're full of little magnetic moments, little atomic current loops, electrons orbiting a nucleus, electrons spinning, and then all those line up and give you a big magnetic field. Well, it's not that simple necessarily. Imagine we had a magnetic moment here. Mu is that way. We can figure out the direction of the current. Oh, it must be this way. It's going around like that because we've been thinking about this a while. What if we had another one next to it? Which way does it want to go? Well, let's see. Magnetic moments like to align with a field. This creates a field going like that. Actually, this one wants to align down. So they don't necessarily want to align. Of course, if we had another one here, it would want to align. So even in our extremely simple little model, we already run into trouble on getting all these things to align. And then, of course, you know, in real materials, they aren't all magnetic. Not everything is magnetic. Let's look at a few materials and see if we can get some feel for what's a magnet and what isn't. So this is a magnet. This is a bar magnet. I painted one end green so we can keep up with the North Pole and the South Pole. And just on my way over, I grabbed a bunch of stuff, and we'll see what's magnetic. So first, I've got a leaf. This is from an oak tree. On my way over, I don't think it minded if I have a leaf here, and okay, leaf is not magnetic, okay. Then I have, in my office, I have this giant piece of calcite. It's a very beautiful piece of calcite that I bought for $6, and no one will ever guess where I bought this piece of calcite. Guarantee. I'll give you 100 years, you'll never guess. Of course, I didn't think anybody would know who Andrea Plan B is either, and somebody did, so I could be wrong. Here it is, big piece of calcite. Any magnetic action with the calcite? No, nothing. Calcite, not magnetic, check. Okay, let's keep looking. Here is my Alamo pillbox. Let's see if we have any magnetic action here. Ah, magnetic. Something about this magnetic pillbox. Both sides too. Let's check this in. Yeah, very magnetic, check. Maybe all metals, right? Let's see. Got in here. Here's a piece of tin foil. This is aluminum. It's very light. Should easily show any magnetism. Nope, nope, not the tin foil. Here, maybe you need a good metal. Here is a piece of copper wire. Copper, magnetic? Nope, nope, nothing going on. No to the copper wire. Finally, here are some vintage paper clips that I found in the demo closet. Let's play with paper clips. Now you're saying, yes, this will be magnetic, because we all recall as a child the magnet and the paper clips. So if I take the paper clip here and boom, it jumps. The paper clip is magnetic, whatever that means. The dipole moments must do something interesting in the paper clip. But the paper clip is not a magnet, because we know magnets have north and south poles, and we know that they like to align north to south if you make a chain. If you push two magnets' south poles together, it repels, or if you push their north poles together, they repel. So here, if I bring the paper clip to the north pole, it attracts. If I bring the paper clip up to the south pole, it attracts. It's happy to attract in either case. So it's not quite so simple to just say that the paper clip is a magnet. Right? Let's see if we can figure out some idea of what's going on. Well, to figure it out, we need to look at this a little bit more carefully. So inside the material, there's magnetic moments due to electrons orbiting around atoms. There's magnetic moments due to spin of the electron. And the question is, how are they lining up? Why are they lining up?